You tap a screen in the back of a moving car, and within seconds, a complex transaction occurs. Money moves across continents, GPS coordinates sync up, and a driver is dispatched to your exact location. It feels seamless, almost like magic. But instantaneous global communication is an illusion. There is no direct magical link between your phone and the server dispatching that ride. Every action relies on a highly structured, completely invisible foundation, operating quietly beneath the surface. By examining the rigid framework hidden inside our devices, we can understand exactly how modern global commerce survives billions of daily interactions without collapsing into absolute chaos. To see why this framework is necessary, we have to look back to the early days of computing. Machines were completely solitary. They existed as isolated monoliths in basement laboratories. The core issue was language. A computer built by IBM operated on completely different proprietary code than a computer built by a rival manufacturer. Because they spoke completely different languages, they physically could not communicate with each other over a wire. Information was trapped in local silos. If you wanted to share data, you carried it physically across the room on a magnetic tape. Building a unified global network under these conditions was a mathematical and physical impossibility. To achieve any sort of digital expansion, manufacturers had to abandon the idea of hardware supremacy. Humanity needed a universal digital language. The solution that finally broke through those early hardware boundaries is known as the TCP/IP model. TCP/IP is not a physical piece of technology. You can't hold it. It is entirely a standard framework, a universally agreed-upon set of rules that engineers adopted to govern how machines talk to each other. Look at this model. The core philosophy of TCP/IP is to take the massive, overwhelming complexity of network communication and divide it horizontally into 4 distinct, manageable layers. By forcing every piece of data through these 4 steps, engineers created a collective architecture. It bypassed the restrictions of proprietary hardware and democratized data transfer for everyone. Taking a closer look at this diagram, the very top section is the application layer. This is the only part of the process you ever actually see. It is the interface providing direct network services to the software running on your screen. Watch as these abstract services shift into specific, recognizable protocols. We have HTTP and HTTPS for web browsing, SMTP to handle your email routing, and DNS to translate web addresses into numbers the machines can actually read. Moving one step down the stack brings us to the transport layer. This acts as the manager between 2 communicating devices, taking raw data from the application above and packaging it into standardized containers. Notice how this layer splits into 2 distinct pathways. These represent the 2 main transport protocols, TCP and UDP. There is a constant trade-off here between reliability and speed. TCP guarantees reliable delivery by obsessively tracking and verifying every single container. UDP, on the other hand, sacrifices reliability entirely, throwing data as fast as possible without waiting for a receipt, which is why your live video streams sometimes glitch but rarely buffer. Regardless of the path chosen, the transport layer has one job: taking chaotic raw data and organizing it into a trackable shipment ready for the wild. Focusing on the 3rd layer down, we reach the internet layer. This level takes on the massive logistical challenge of routing data across a decentralized global map. Here, you can see the packet actively stamping itself with a specific IP address. By utilizing these unique numerical coordinates, the internet layer calculates the most efficient route and navigates the data precisely to its intended destination. Dropping to the very bottom of the stack, we hit the final foundational step, the network access layer. This is where theory turns into brute physical force. The network access layer handles the actual hardware transmission, converting the data into electrical pulses down Ethernet cables or radio waves across local Wi-Fi. Following the waveform to the receiving device, the journey completes. The data arrives, enters the bottom of the receiver stack, and descends back up through the 4 layers to become usable software again. Sending data across an ocean or a local coffee shop utilizes the exact same mechanism. This specific 4-layered gauntlet is what guarantees data survival and integrity across any physical medium on Earth. It's worth noting that the survival of TCP/IP was not guaranteed. During the early days of networking, it had a massive historical rival known as the OSI model. If we place them side by side, you'll see a rigid 7-layer stack next to the streamlined TCPIP version. The OSI model was a highly theoretical ideal designed by international committees trying to account for every possible networking scenario. But TCPIP ultimately won the protocol wars because it was bare bones and implementation focused. While committees debated the theoretical perfection of the 7-layer model, engineers were already using the 4-layer model to solve real-world problems immediately. The modern internet was built on engineering pragmatism. The standard that worked in practice defeated the standard that looked perfect on paper. Returning to the modern day, we can see the result of that pragmatism. The global digital economy is an endless, interconnected motion. This sprawling society functions solely because every single smartphone, every server farm, and smartwatch on Earth bends to the rules of the TCP/IP framework. True, world-spanning scale is rarely achieved through proprietary control. It is built through flexible, shared standards that simply allow humanity to connect.